Hello, so good afternoon to all, and welcome to this particular lecture where I am going to discuss about the diode characteristic. So this lecture I am going to start with the diode characteristic, and over there I will draw the characteristic and also mention the equation, Shockley equation, which is used as the mathematical equation for the diode characteristic. I will then discuss about the difference between the ideal and the practical diode, and from this I will then come to the equivalent circuit, like how the actual diode characteristic can be converted into the ideal characteristic. And from there, then we will move to the load line analysis, which is used to solve any circuit having diode as one of the component. And from this, then we will discuss some of the problems, circuit problems, and how to solve them. So starting with the diode characteristics. So for the diode characteristics, and participants, like, you can ask your questions by typing in a comment box. So if we talk about the diode characteristic, we know that the diode, like if I draw, this is ID, this is VD. So if our diode, like if this is our diode, and if this diode, this is P side, this is N side, means this part it is P type material and this part it is N type material. So we know that if this P type material, if it is connected to the positive terminal of the battery, then the and negative terminal is connected to N type, then we say that our diode is forward biased. Forward biased, right? And for this forward biased, we will in this lecture I am not going to go into the physics of the depletion layer and the movement of the electrons holes. So directly I will draw the characteristic that for the forward bias, the characteristic it is drawn somewhat like this. Right, over here means in the starting when the voltage is zero, over here VD is 0 volt, right? So when the voltage is zero, then there is no current. But even after, when we increase this diode voltage, means when we increase this voltage, then also the current across the diode, means this is the current ID. So the current through the diode, it is not increasing, means there will be high resistance. This diode will try to stop the current. But after some certain voltage, let it be Vk. So after this voltage, then by increasing the current, if we increase the voltage greater than Vk, then we see that there is a sudden increase. There is a sudden increase in the current. And this Vk, it is known as knee voltage. It is known as knee voltage. So knee voltage is the voltage after which diode start allowing the current through it. Means the conduction of the current starts flowing. Conduction of the current established after Vk, after knee voltage. Before the knee voltage, current will be very very less, that we can simply ignore it. It is negligible. The current, usually the current that is flowing through the diode, it is measured in milliampere, but it can be anything. As you can see that why it is in milliampere, because in the starting when we are increasing the current, the voltage at this point the level of the current is too less. The level of the current increases only after new voltage. So to determine the current, what is the current flowing in this region, we measure the current in milliampere. But it can be like in this region, like it can be in amperes also. When we talk like this same diode, when it is connected in the reverse biased, like this, means the negative terminal, it is connected to this P side of the diode, positive, means P type of the material of the diode, and this positive terminal of the battery is connected to N type. In this case, this diode is reverse biased. Reverse biased. And in this reverse biased, if we draw the characteristic, then the characteristic, let me use different color. So the characteristic, it will be somewhat like this. And this negative part, it is measured in either microampere or picoampere. Microampere means microampere, or microampere it is equals to 10 power minus 6 ampere, and picoampere it is equals to 10 power minus 9 ampere. So you can imagine that how low this current is. So if during the so we can see that in the reverse biased, in when the diode is in reverse biased, it is simply we can ignore this current. This current can be ignored, right? And we treat the circuit as open circuit. So when the diode is connected in the reverse biased, then this current, it is known as IS. This, it is IS, right? And this IS, it is known as saturation current. Saturation current. Why it is known as saturation current? Because because as you can see, just the level of this is not increasing, the current is not increasing, it is same. Means as we increase the voltage in the negative side, then also the current is not increasing, and since the current is not increasing, so it means that the current has reached its maximum level. So it is the reason it is known as saturation current, and we represent it with IS. Now, if we increase the current voltage, if we increase the voltage further, then what happens at some particular voltage, there is a sudden increase in the current. In the reverse bias also, there is a sudden increase in the current, and this voltage, it is known as VR, which is breakdown voltage. At breakdown voltage is the voltage in the reverse bias at which the diode starts conducting the current. There is an avalanche breakdown or the Zener breakdown, and at this region the diode starts conducting immediately in such a way that the resistance over here, it is too high, is high, right? So this is the characteristic of the diode, that in the forward bias the behavior of the diode will be represented by this curve, whereas in the reverse bias it will be represented by this curve. If the voltage has increased beyond BR, then there will be a sudden increase in the current, and the current or the characteristic or the behavior of the diode will be determined by this. Right. Now this complete characteristic, it is defined by the Shockley equation. Let me let me erase this a little bit. Shockley equation. Right. Now what is Shockley equation? Shockley equation is defined as ID is equals to IS bracket e power raised to the power VD upon neta VT minus 1. Right? Or this complete, or let me write it again with some improvement. It is VD divided by neta VT, and this is minus 1. Right? Now over here, this ID is the diode current, means the current that is flowing through the diode. This Is, it is the reverse saturation current. This Vd, it is the diode voltage. This then N or eta. This N, this factor N, like this is equals to 1 or 2, means its value ranges from 1 to 2. And typically, like it depends on the characteristic, on the construction and physical construction of the diode. And typically, like if nothing is mentioned, that we simply take the value of N as 1. Vt, it is known as thermal voltage, and it is expressed as Kt by Q. Kt by, just a moment, Kt by Q. Now over here, K, it is the Boltzmann constant, constant, and it is equals to 1.38 into 10 power minus 23 joules per Kelvin. T, this T, it is our temperature in Kelvin. And Q, it is the charge of the charge carrier. And since in the diode we have charge in the form of electron or holes, so the charge is always equals to 1.6 into 10 power minus 19 coulomb. Right? Now over here, if you substitute all these values of K, Q, and if you consider like at room temperature, at room temperature, which is equals to 27 degree, or sometimes like we take it as 25 degrees, sometimes 27. So if it is 27 degree, it means it is 300 Kelvin. So if you substitute this temperature, the value of T in this equation, the value of K is constant, the value of Q is constant. So if you substitute all this value in this equation, then you will get your Vt as 26 millivolt. 26 millivolt. So you can imagine it, this VT, it is quite very less voltage, right? Now, if we again come to this particular equation, so now if like this particular equation, it can be opened, like we can open the bracket, and if you open the bracket, this equation becomes ID equals to ISE VD upon neta VT minus IS. Okay, so I simply open this bracket, so IS is taken inside. Now, for the forward biased, this VD, this VD will be positive, right? For the forward biased, let me change the ink. So forward biased, right? So for the forward bias case, our VD, it will be greater than 0, right? Now VD upon neta VT, VD upon, or let me put it in the another page. So our equation, it is ID equals to IS e power Vd upon neta Vt minus Is. Now considering the forward bias case. Now for the forward bias case, our Vd, it is greater than 0, right? Now suppose if Vd is equals to like if Vd is equals to Vt, means 26 millivolt, then then our E Vd upon neta Vt, and if n is taken as 1, then this will be equals to e power 1. So if Vd is equals to Vt, means if Vd is equals to just 26 millivolt, right? 26 millivolt is 0.026 volt, means very very less voltage. Then our power of E, it will be 1. If Vd is equals to 2 Vt, then exponential, it will be 2 Vt upon Vt, right? So we will get e power 2. If Vd is equals to 3 Vt, then our exponential, it will be 3. Now what is e power 1? E power 1, it is like numerically, if you use the calculator, you will get e power 1 is 2.7, e power 2, it is 0, uh, it is 7.4, and e power 3, it is 20. And remember, it is unitless because over here in the equation this is Vd divided by Vt, right? And since the two voltages are getting divided, so we do not have any units, right? So now if we look at this values 2.7, we get power 2.7 just when the Vd is too less, just at 0.026 volt, we are getting e power 1 as this, right? So if we substitute this value, if we substitute this value in this case, means this formula will become like for Vd equals to Vt. This formula will become Is, or for this case, let me take the brackets in, right? Presently, we do not need to open the brackets. So it is like this, right? So it is e power, and when Vd is equals to Vt, for this case, we are getting e power 1 minus 1. Now this is Is 2.7 minus 1, right? So Id is equals to 2.7 minus 1, and this is true for just this very small amount of voltage. Now when Vd is equals to twice of Vt, in this case Id will become Is and e power 2 minus 1. E power 2 is 7.4, right? So this will become Is 7.4 minus 1. For Vd equals to 3 Vt, our Id, it will become Is e power 3 minus 1. So it will be Is 20 minus 1. So and this we can approximately write this as Is into 20. Means we can skip this one. Why? Because even if it is thrice, if it is three times of Vt, so it is just 3 into 26 millivolt. Means it is just 18 and 78. It is 78 millivolt, means 0.078 volt. So it is very less, and at very less we are getting this 20. So you can imagine when we are going to provide like zero point 0.1, when this voltage, when Vd is equals to 10 times of Vt, right? Then this term e power 10, it will be too high, right? So simply we can ignore this one, we can ignore this one from the equation. So for the forward bias, we can approximate our equation to be like Is e power Vd upon neta Vt, right? And now if you look at this equation, our equation is Id equals to Is e power Vd upon neta Vt. So due to this exponential term, our our characteristic, our forward bias characteristic, it comes out to be like this. It is coming out in the form of exponential. It is exponential, just it is exponential increase in current, right? This is VD. So means just in the forward bias, we can ignore -1 and our equation is something like this. And this equation is representing this exponential term. With this, we proved that the Shockley equation which is defined as this, by this, it is true for the forward characteristic. Now similarly we will look for this equation for the reverse bias. Now for the reverse bias, like again if I write the Shockley equation, it is is e power vd upon neta vt minus is, right? Now over here, since we are going to provide for the reverse bias, VD is less than 0. Since it is less than 0, so our equation can be written as ID equals to Is e power minus Vd upon neta Vt, because whatever voltage that we are going to provide, it will be in minus. It will be in minus. So it will be this. Right? Now over here, again for Vd equals to Vt, the term will be exponential term will be -1. For Vd equals to 2Vt, the exponential term will be -2. Right? So, and for -1, the value is 0.37. For this power -2, the value is 0.14. Now, if I substitute, means over here, again, I guess we just a minute. Yes. Okay, just let me take the brackets again. -1. So this is, so it means when VD is equals to VT, in that case our ID, it is equals to IS. Within the bracket, this exponential term, it is 0.037. So 0.37 minus 1, right? 0.37 minus 1. So, and when VD is equals to twice of VT, in that case ID, it will be equals to IS 0.14 minus 1. So, and this we can write it approximately as minus of is, right? So you can imagine, like similar to the previous discussion for the forward bias, like vd is equals to twice vt, and just at this point, which is very very less, right? For this we are getting this term which can be approximately written in this form, right? Means we can ignore this exponential term from the reverse biased, right? So if even if we ignore this reverse exponential term from the reverse bias, we are getting a approximately we are getting a good value, right? So because as we increase, like when vd is equals to 10 of vt, this exponential term will become -10, and this e power -10 will be very very less. Like if it is 0 point, it may be like 0.0001. So you can imagine that this number is very less in comparison to this one, and hence this exponential term, it can be ignored. So for the reverse bias, simply we can write that for the reverse bias, our approximation is that id is equals to is, right? So for the reverse bias, id is equals to minus of is. And same thing, like if you like go back to the characteristic curve for the reverse bias, we had drawn that our in the reverse bias, our current is like this. This is our is, and this is, it is is over here minus is. This is vd. This is VD, right? So same thing is reflected by this equation. So overall, what we can conclude that this Shockley equation correctly represents the characteristic of this diode. Means this diode characteristic, this complete diode characteristic is represented correctly by the Shockley equation, right? So mathematically, if we want to determine what is the voltage or what is the voltage across the diode or what is the current through the diode, in that case we will use this Shockley equation. But and graphically, if we want to determine the voltage or the current graphically, then we will use the characteristic curve, right? So if you have any doubt, you can put it in a comment box, right? Now coming to the next, where I will tell you what is the like ideal diode versus versus practical diode. And as the name is itself, name is saying the ideal diode. Ideal diode is something that we want to achieve, and practical diode is the one that we actually have and have some limitations, right? So over here, when we talk, like if I put if I draw a symbol of this diode, practical diode. Now from the characteristic, we know for the diode, we know that in the forward bias, when we increase the voltage, when we increase the voltage, so in the starting, the current will be very near to zero. And after the knee voltage, then the current will start increasing. So means at this, after this knee voltage, when we increase the voltage across the diode beyond knee voltage, then there is a exponential increase in the current, right? So what it means? It means that this diode, practical diode, is not conducting. It is not conducting the current till knee voltage. So let me write practical diode is not conducting any current till knee voltage. Till knee voltage, right? And beyond knee voltage, then it starts conducting the current, and the current is increasing exponentially, right? Current is increasing exponentially. Now similarly, for the reverse biased, as we have already discussed, the current, it is in this form, and this current is is, and this is, it is in it is in micro amperes or pico amperes, means it is too less that it can be ignored if the current in the circuit, if it is flowing in milliampere, then it can be ignored, right? This is very less current. So it means that in the reverse bias, we can say that we do not have any current, we do not have any perceivable current, right? So simply overall, what we can conclude with this, that the practical diode, it is conducting the current only after knee voltage. So up to this knee voltage current, we can say assume we can approximately assume that current is equals to zero. For the reverse bias, we can approximately assume that our current is zero, right? Only after knee voltage, we have current. We have current. We cannot assume it as zero, right? Now when we talk about the ideal diode, what we want in the ideal diode, we just the symbol is same. Only thing is we used to represent it as ideal. And in the ideal diode, simply we draw the characteristic in this way, that beyond less than zero, when this VD is less than zero, we assume that ID is equals to zero. And for voltage greater than zero, we assume that that the current is increasing at 0 degree only. Means the knee voltage for the ideal diode, the knee voltage is 0. Right? For the practical diode, we have some knee voltage. Like for silicon, Vk is equals to 0.7. For germanium, Vk knee voltage it is 0.3 volt. For gallium arsenide, our Vk knee voltage it is equals to 1.2 volt. But for the ideal diode, for the ideal diode, our Vk is assumed to be 0. And also Vk is 0. Also Is is assumed to be 0. So it is 0 volt, it is 0 ampere, right? It is 0 ampere. So this, if we assume this, it means we have assumed that our diode is an ideal one. So this is the difference between the ideal and the practical diode. And why it is necessary? It is necessary because as we see that our diode characteristics, this diode characteristic, it is non-linear. Why non-linear? Because we know, like suppose we know that for a resistance follows Ohm's law. Right? Ohm's law means it follows Ohm's law means that if we draw a graph between say I and V, then it will be a straight line passing through the origin. Main thing is that it is this straight line, and since it is straight line, we say that it is linear. V is linearly proportional to I, or I is linearly proportional to V, so it is linear. But for the diode, we have the characteristic non-linear. Like in the forward bias it is like this, it is non-linear, and in the reverse bias it is like this, again it is non-linear. And since it is non-linear, so our diode it is non-ohmic, right? But it is non-ohmic, but like as we have seen the circuit having the resistance. See, when we follow the Ohm's law, circuit analysis becomes simple. So we would like to convert this non-linearity into the linear circuit somehow. So if somehow if we are able to achieve this linearity, then we will apply the Ohm's law even for this non-ohmic material, right? And once we start applying the Ohm's law in the diode, then we can treat the diodes very similar to the resistor, and our circuit calculation becomes simple, right? So it is the reason that we are trying to approximate the practical nature of the diode to the ideal diode. And apart from the ideal diode, like by including some other things also, we can at least approximate it, not as ideal diode, but as linear diode, right? So how we can do that? This can be done by drawing the equivalent circuit for diodes, or diode equivalent circuit diode equivalent circuit. So what is this diode equivalent circuit? Now over here we have three types of diode equivalent circuit. One is known as piecewise, linear equivalent circuit. Second is known as simplified equivalent circuit. And third is known as ideal equivalent circuit. So first we are going to obtain the piecewise linear equivalent circuit. Then from piecewise we will move to the simplified, and from simplified we will move to the ideal. So now if we come back to our diode characteristics, diode characteristic, It is like this. Now, if this little bit, what we can do? If I put this line like this, just this line will be approximately a straight line. So this red line is representing our piecewise linear equivalent circuit. Piecewise linear equivalent circuit. And this purple, it is our practical diode. Now what is it is showing? Now over here we know that it is the knee voltage, right? It is the knee voltage, right? This is VD, this is ID. So what approximation we have done in this piecewise linear equivalent circuit? The approximation that we have done is that we assumed that over here before voltage before VK, VD less than VK, voltage less than Vk, in practical diode current is not exactly equal to zero. It is increasing, but the increase in the current is very less, right? So, but it is not zero. So, in practical diode, it is not zero, but in piecewise linear equivalent circuit, we assume that it is zero, right? So if we like make a practical and piecewise. So if we talk about the knee voltage or VD less than knee voltage, so the current ID is not equal to zero. But in piecewise, we assume that ID is equals to zero, right? So in piecewise, we have taken this approximation that the current is not increasing slowly, exponentially, right? We assume that current remains zero. And after Vk, when Vd is greater than Vk, now in this case, in the practical diode, it is increasing. The current is increasing exponentially. It is increasing exponentially. E raised to the power Vd upon neta Vt minus 1, right? But in the piecewise linear equivalent circuit, we just represent this increase by a straight line, by a straight line. And we know that, like if we talk about against the Ohm's law, it is like V, it is I. So we know that it is this is the slope, and this slope of this line, slope of this line. What it represent? It represents resistance. It represents resistance. So if by showing this, by representing this curve by a straight line, what we are doing, we can represent this straight line with a resistance, and this resistance is known as RAV, or the average, or the average resistance, right? So just the characteristic curve, or forward characteristic curve of the practical diode, it is approximated as a horizontal line before Vk and a slant line after Vk. The slant line is showing the resistance, whereas the horizontal line shows that ID is equals to zero, right? So how we can represent this in the circuit? Now in the circuit, if this is our practical diode, this is our practical diode, Then our piecewise linear diode, it can be represented as, first we will represent it with Vk, with plus and minus, right? So this is A terminal, this is A terminal, right? Then after Vk means up to Vk there will not be any current through the circuit. Now after Vk, this straight line is represented by a resistance, which is represented as RAV. 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 And then we have the idle diode. Then we have the idle diode. This is ideal. And this terminal, it is P. Same as this. So So over here, whenever we want to represent our diode, this practical diode in terms of piecewise linear equivalent circuit, so simply in the circuit, we will replace this practical diode with these three components. These three components are Vk in this form, plus over here, minus over here. Just remember that on the P side of the diode, we put plus, on the N side, we will put minus. So we replace the practical diode with the knee voltage followed by the resistance followed by the idle diode. And for the idle diode, we know one more thing. Sorry, I forgot to mention one thing, that in the idle diode, as I mentioned over here, for the idle diode, when Vd is greater than zero, then it is current is flowing. So we can represent our idle diode as closed circuit, closed circuit when Vd is greater than zero. So when Vd is greater than zero, then idle diode can be replaced with the short circuit, simply short circuit. Whereas this idle diode, it can be represented as open circuit when Vd is less than 0. Why? Because when Vd is less than 0, like in this case, when Vd is less than 0, then our current is 0. So overall, our idle diode, it can be represented, it will be replaced with the closed circuit when we applied a positive potential. When idle diode is forward biased, we represent our idle diode as a closed circuit, and for a reverse biased, our idle diode will be represented as open circuit, right? So this is what we are going to do over here, that when the potential across these two terminal, this C and D, when the potential across C and D, when C is positive, D is negative, means C is at high potential in comparison to D, then this ideal diode will be replaced with the straight wire, means closed circuit. And when C is at low potential in comparison to D, then this diode will be replaced with the open circuit. Right? So for this first case, for this piecewise linear equivalent circuit, if we want to represent our practical diode as piecewise linear equivalent circuit, it means that simply we will replace our diode in the circuit, we will replace our diode with this Vk, Rev, and the idle diode. Now from this, we will then